Okay, let's do problem number 3 from the midterm exam now. And so problem 3 says consider an air parcel at sea level on the coast of the island of Luzon in the Philippines. The air parcel has a temperature of 30 degrees and a relative humidity of 100%. The parcel is lifted to a maximum elevation of 1,400 meters over the Cordillera Central mountain range. It then descends through the mountain town of Baguio to a final elevation of 800 meters. And the question asks us to determine the following. A, the temperature of the parcel at the top of the Cordillera Central. So this location here, B. The final temperature when the parcel descends to its final elevation of 800 meters. And then the relative humidity at its final location, location C here. Okay, so a really important insight into this problem is that the parcel is saturated to begin with. So its relative humidity is 100% at an elevation of 0 meters when it's on here on the coast, and it has an ambient temperature of 30 degrees. Okay, so the insight that we want to glean from this is that because the parcel is already saturated, as it's lifted up and over the Cordillera Central Mountains in the Philippines, it will be subjected to the moist adiabatic lapse rate. So unlike the problem in the class and in the lab that you saw, there's no need to sort of figure out the lifted condensation level of this parcel. It is saturated when it starts, and therefore the lifted condensation level, another way of looking at this, is at an elevation of 0 meters. And so the key facet here, or the key insight, is that we don't need to sort of stop and determine this elevation at which the parcel saturates and then proceed to lift it along the moist adiabatic lapse rate like we did in the lab. We can just proceed to lift this parcel up 1,400 meters at the moist adiabatic lapse rate. Okay, so what does this look like? Okay, so for part A, we're going from location A to B. Okay, and the equation that we need here is the temperature at location B is just equal to the temperature at location A plus the change in elevation, delta Z, times a lapse rate. And again, because this parcel is saturated, we use the moist adiabatic lapse rate here. Okay, so if we plug the numbers in, we get 30 degrees C plus delta Z is 1,400 meters, and the moist adiabatic lapse rate is minus 6 degrees Celsius per 1,000 meters. Okay, so when we turn the crank, we get a temperature of 21.6 degrees Celsius. And that is the temperature of our air parcel once it reaches the top of the Cordillera Central. Okay, so for problem B, which is asking us to determine the final temperature of the parcel when it descends to its final elevation of 800 meters. Okay, again, the key insight that we have is that as we go, or as we get to the top of the mountain, so at location B, the parcel is still saturated with a relative humidity W equal to 100%. But at a new temperature, which is 21.6 degrees Celsius. Okay. So now the insight that we want to apply in this problem in taking this parcel from an elevation of 1,400 meters to an elevation of 800 meters is that as soon as we start descending that parcel from the top of the mountain range, it will become unsaturated. Okay, so the temperature increases ever so slightly, the relative humidity goes down just a little bit, and so we will be descending this parcel at the dry adiabatic lapse rate. So to determine the temperature at the final location, at location C, we apply the same equation. So temperature at C is equal to the temperature at B plus delta Z times a lapse rate. But here we will be using the dry adiabatic lapse rate. So when we plug in our numbers here, we get temperature at C is equal to 21.6 degrees C. This was what we determined from part A. We're going down in elevation 600 meters, so from 1,400 meters to 800 meters, and we are subjecting our parcel to the dry adiabatic lapse rate of minus 10 degrees Celsius per 1,000 meters. So the meters here cancel out. We're left with degrees Celsius. When we turn the numerical crank, we get a final temperature at location C of 27.6 degrees Celsius. Okay, so finally on to problem 3C, in which we're being asked to determine the relative humidity at location C. Okay, so there's a couple of really important insights here that we need to apply. So the first off is just our definition of relative humidity. So the relative humidity at location C will be equal to the actual vapor pressure at location C divided by the saturation vapor pressure at location C times 100%. Okay, so one quick insight here is that the saturation vapor pressure at any location is always equal to or only a function of the air temperature of that location. So if we know the air temperature at location C, which we just calculated from problem B, then we can determine what that saturation vapor pressure is. So why don't we go ahead and do that? So we'll use our equation EC at saturation is equal to 0.611 kPa times exponent of 17.3 times 27.6, which is what we got from problem B, divided by 27.6 plus 237.3. Okay. And when we do that calculation, we should get E sub C at saturation. The saturation vapor pressure, the total amount of water that the air parcel can hold at location C, is equal to 3.71 kPa. Okay, so this is an important thing that we'll need to keep for our calculation. Okay, so we also need to determine what the actual vapor pressure is at location C. And this is where we need to apply some reasoning about our parcel. So to determine the actual vapor pressure at location C, what we need to understand is that when that parcel got to the top of the mountain range at location B, it was saturated, and it was saturated at a temperature that we calculated in part A. And then as it traverses down, as it descends from an elevation of 1,400 meters to 800 meters, there's no mechanism through which we remove any more water from that air parcel. Okay, so it turns out that the vapor pressure at location C is just equal to the vapor pressure at location B, right? So as the parcel goes from B to C, there's no mechanism through which we can remove additional water as it's descending at that dry adiabatic lapse rate. Okay, so what is the vapor pressure at location B? Well, it turns out that, again, the parcel was saturated when it got to the top of the mountain range. So, and if we understand what that means, what the implications of that are, we can say that the relative humidity at location B was 100%. But the definition of relative humidity is just E sub B over E sub B at saturation times 100%. And we can say, therefore, EB is just equal to EB at saturation is equal to the vapor pressure at location C. So this is the crux of how you get the relative humidity at location C. Because now, it turns out, all we need to do is determine the saturation vapor pressure at location B, which is a function only of the temperature at location B. Okay, so we could say EC is equal to EB sat, which is equal to our equation here again, 0.611 kPa exponential (17.3 times 27.6). And again, that's the number that we got from problem A, 27.6 plus 237.3. Okay. Sorry, sort of ran out of space there. Okay. When we use this equation to calculate the saturation vapor pressure at location B, or the vapor pressure, the actual vapor pressure at location C, we get a value EC is equal to 2.59 kPa. Okay, so now to combine these, remembering our definition, we would say EC and EC sat, which we previously determined, and we get a value of 69.8%.